everybody. In today's video, we will be talking about Coulomb's law. In the last video, we talked about charge and charge conversion, and we all know that there are three basic charges: the positive charge, the neutral charge, and the negative charge. Coulomb's law states that the charges with like signs, meaning positive and positive, or negative and negative, they will both repel. But charges with opposite signs or unlike signs, such as positive and negative or negative and positive, they will attract. Now there's actually a bit of a misconception here because Coulomb's law does not necessarily state what happens to a neutral charge. But let us all remember that there is no such thing as a totally zero charge, except in a subatomic scale, but there's no such thing as a neutral charge if you place it into a higher matter. So it will always have the same number of positive charges and negative charges if it were a neutral charge. So it would be like this. This is just a rough sketch. However, if you place, say, a negative charge near it, what happens there is actually the electrons will be repelled to one side, leaving one side to be more positive than the other. So it would become the picture at the bottom. It would become more like this. However, it's still electrically neutral. That's why, since this side is more positive than the other, and it's nearer to the negative charge that we introduce, this will also attract. So we could also say that positive and neutral attract, neutral and positive attract, neutral and negative attract, and finally negative and neutral also attract. Now, the reason why they are attracting or repelling each other is because of something we call the electric force. Electric force. Now, if you guys know the formula for Newton's universal law of gravitation, which is equal to negative gm1 m2 over r squared, it is similar to the electric force. Take note that this is gravitational force. It is only similar to electric force. Now, the electric force can be between two objects can be written as K Q1 Q2 over r squared. Now K is a constant which is equal to 8.988 times 10 raised to 9 Newton meter squared per Coulomb squared. R is the distance between the two charges, and Q1 and Q2 are the values of the charges themselves. Now, since this is a force, this is actually a vector quantity. So meaning it has both magnitude and direction. So we can use vector notation to solve for two-dimensional problems using electric force. Now, actually, I have just the problem for that. Let us move on to the example problem. In the example problem stated, we have 4 charges of equal magnitude positioned on a square with side length 0.75 meters. So let's just draw that. So these are the 4 points in the square, and this is 0.75 meters and 0.75 meters. And now a negative charge is positioned in the upper right corner of the square, and the rest are positive charge. Take note that they are in equal magnitude, so let's just say Q. So that's negative Q, this is positive Q, and positive Q. What is the magnitude and direction of the force acting on the charge on the bottom left corner of the square? So we're looking for the force acting on this, net force. So let's make a free body diagram first. This charge is being repelled by this charge, so let's call that F1. This charge is being repelled by this charge, so let's call that F2. And this charge is being attracted by this charge, let's call that by F3. Now this is 1, this is 2, and this is 3. So how do we do this? Well, the most basic thing that we could do is, first we should take the distance between this, but since this is a right triangle, because it's positioned in a square, this is a right angle, we can use the Pythagorean Theorem. This would be equal to 0.75 square root of 2 meters. I'm just placing there the square root of 2 for now, so that computations will be simpler. We could just do every radical at the end of the computations. So here, we could notice that this is a right angle. So what we could do is we could translate F1 to be here. It would still have the same value. This will be F net 1, 2, meaning the total force between forces 1 and 2. So since they're equal, F1 is equal to F2, which is equal to KQ squared. I'm saying Q squared because all of them are equal, divided by 0.75 squared. Now since that would be the legs of the right triangle we have here. So F net 1, 2 would be equal to, just use the Pythagorean Theorem again. I'm just going to compute it already. So this becomes KQ squared, square root of 2 over 0.75 squared. Again, we will be computing all radicals at the end. Now, one more thing is F3. We have to find F3. That would be equal to, well, let's just say since we already have the direction, we just need to find the magnitude. So this becomes KQ squared, since both of them are of magnitude Q, over 0.75 square root of 2 squared. Well, that just becomes 2 times 0.75 squared. Now we just need to add both of these. Take note that this is actually negative because it's an attractive force. And all attractive forces are negative in sign. So we just need to add both of these. This becomes K q squared square root of 2 over 0.75 squared minus kq squared over 2 times 0.75 squared. Now, since we're dealing with fractions, we take the cross multiplication of this. This becomes 2 square root of 2 times kq squared minus kq squared all over 2 times 0.75 squared. Simplifying this further, we can factor out kq squared, and this becomes 2 square root of 2 minus 1 all over 2 times 0.75 squared. Now take note that k is 8.988 times 10 raised to 9 Newton meter squared per Coulomb squared. So, leaving it in terms of q, we would get the value of 1.46 times 10 raised to 10 q squared newtons. And that would be our final answer. So, thank you for watching this video, guys. If you have any questions, please leave them in the comment section below, and also like and subscribe to my channel. I would greatly appreciate it if you do. And if you want me to cover a topic in one of my future videos, just leave them down in the comments. Again, thank you and have a great day.